Okay, so we are ready for the last presentation of this workshop week, where I'll go through the how the software works for data analysis of profiles verbally. Okay, so this will be a mix of a presentation and a demonstration of the software. I'll start with the presentation. So when you install the SensorTrace software, then you will have a set of demonstration files installed with it. And those are the files that I will use today. So you can actually repeat this at home if you want. There is a file calling profilingdemo.upro that is saved as a read-only file in the Documents Unisense Data Demo Experiments folder, like you can see here. That's the one I'll work with in a moment. We also have a profiling application note, which I have mentioned before. You can download that from our website. I'll also show it here. So this is, I think, a 6 pages flyer where you can read how to do the analysis. And this analysis is also made on the demo experiment profiles here. Yeah, so just briefly, you go to unisense.com, the knowledge part, application notes, biogeochemistry, and then you find the sediment profiling analysis. So first, the profiling analysis can be done in the activity part of the software. What you will get is something similar to this, where you have a profile measured, the blue dots, and you will get a fitted curve, the orange line here, and you will get the calculated production and consumption rates. It has a funny oriented scale, so it starts with positive to the left and negative to the right. So this one is positive in production, this one is negative in consumption. And then you'll get some statistic parameters out as well from the fit. So you will need to define a number of variables, so to lock some boundary conditions for the software to work. And you will need to also specify the diffusion coefficient and the porosity of the sediment for this to work. And I showed this yesterday, I'll just go through it again. So what you can get from a microprofile is, first of all, the part that is a straight line up here, that is in the diffusion boundary layer. So the layer where water is stagnant, so the diffusion is the only transport process. And if there's no consumption or production, a straight line indicates diffusion only. So the concave part of the profile here, that indicates there's production, and the convex part down here indicates there's a consumption. This is sort of the calculated rates over here, consumption and production here. Bit more into detail. So the quantitative information you can get from this is, first of all, you can get exactly what is the concentration in the sediment where your organisms are living, and maybe if there's overlap between different analytes you've measured, so on. Then you can do flux calculations using Fick's first law of diffusion. So it's simple in the water. That is in diffusion boundary layer. You calculate the slope, the dCdx of your profile here, and multiply that with the diffusion coefficient of your analyte in water. And then you get the flux through the diffusion boundary layer. In sediment, you need to take into account that there's a part of the volume is taken up by particles. And that makes diffusion less efficient. Therefore, you need to multiply with the porosity, which is the same as the water content, and then the diffusivity. And the diffusivity can be calculated in different ways. Simple form is you simply multiply the diffusion coefficient for your analyte in water with the porosity. But there is, I'll just spend a moment on this. So in pure water, when you have diffusion, then there's 100% of the space is available for diffusion. If you go into the sediment, you have part of the sediment of the volume taken up by particles, as shown here. For example, if the porosity is 0.8, then only 80% of the space here is available for diffusion, and 20% of the space is taken up by particles. So this that simply reduces the amount of water and therefore also the flux of your solute through this sediment. Then tortuosity has also been taken into account, and tortuosity is a term describing the fact that diffusion has to on molecule has to zigzag its way through in between the particles. And as I mentioned, one way of calculating this, taking this into account, that is the diffusivity, that is to multiply the diffusion coefficient in water with porosity. But there are different ways of doing it, and the software has the options here. So you can actually, the simple one is the porosity times diffusion coefficient. That's the first one here. The second, that is porosity squared times diffusion coefficient. That's more for low porosity sediments, very compact sediments. And then finally, there is a sort of empirically derived equation for how to calculate diffusivity. It's taken from a Bernie Boudreau paper where he's analyzed a lot of sediments. The reference is mentioned in the application note that I mentioned a little while ago. Okay, and so the final calculations you can do here is you can analyze the curvature. That's what the software will do, the curvature of the concentration profile. And by taking the second derivative of the concentration profile, multiplying with the diffusivity and porosity, you'll get the net oxygen consumption. That is sort of indicated with this brownish bar graph here. So the software will analyze profiles measured with Unisense equipment. And that it doesn't matter whether you analyze it or measure it just as I did half an hour ago using a microprofiling system, recording the data right on the PC. You can record them on the field the field multimeter, download them to the software and analyze them, or they can be recorded in situ using either the mini profiler or deep sea profiler, and you can download the data to a PC and analyze the data in the software. And there's different depths you can work with here, and everything can be analyzed in the profiling software. So it's important to know what part of your profile is water and what part of profile is sediment, because you just want to do the analysis on the part of the profiles that in the sediment. So the trick is to know where is the sediment surface relative to all your data points. And there are different ways. The microscope is a good way, so you know where your sensor tip is when you are measuring the profiles. It's not always that is possible. Another way of doing it, at least for the oxygen profile, that is simply to look at the see if you can identify the diffusion boundary layer. And in this case, it looks maybe a little bit stupid, but I've zoomed in on the part of the profile that I think is the diffusion boundary layer, and with a ruler, I can see that they are actually quite linear in this area. And down here, the slope changes, so it becomes more steep. And that's what it should do when you go from the water into the sediment. So a steeper slope here and a less steep slope here. And that's one way of defining it. It requires that you have a good setup, so you actually have a well-mixed water column above the sediment, so that a diffusive boundary layer can develop and be recorded, as was the case here. So we need to do some settings before we can analyze the profile. First of all, oops, that was too much. We need to define the diffusion conditions, so the diffusivity and the porosity. That's shown here. And if we go into detail with that one, the diffusion coefficient of, in this case, oxygen in water is well known from tabulated values in the literature, and this is built into the software. So you just tell the software what the temperature is and what the salinity is, and then it gives you the diffusion coefficient, in this case of oxygen in water. Then you need to define what intervals you're working at. I'll get into this in a moment in the software, so I'll just do it briefly. So in this case, I've taken two intervals going from -1500 to 0, where 0 is then supposed to be a sediment surface, and then below in the sediment from 0 to 1200 micrometer. And there I've defined the porosity, and therefore diffusivity is calculated here from the formula I've selected up here. The formula for porosity, for diffusivity calculations I have mentioned already. So the simple one, porosity times diffusion coefficient, is for high porosity sediments and biofilms, fine sand. More compact model, low porosity, is we recommend using the second one, and the third one is for all kinds of sediments. The porosity is easily determined in sediments simply by slicing the sediment, for example, every 5 millimeters, and determine the weight loss after drying, and then you get the water content. So now I'll shift to the software to demonstrate how to do this. So when you've installed the profiling software, then in Documents, you will find the Unisense data folder, and if I sort it correctly, you will find the demo experiments here. There are different ones. There's a rate for the microrespiration system. There's a logger demo with stocks data. There's a logger demo for just logging, and there's the profiling demo, and that's the one I want to use now. It says it's a read-only, and it's made read-only because you're not supposed to change it. You can always use the file save as and then save changes anywhere else. But the idea is here that you should be able to always have this and to compare it to this application note. So when you open the file with a number of profiles, you see the profiles out here. What I would like to start with is show the visualize, and this is here. A number of profiles have been measured in a marine sediment from a coastal lagoon in Denmark, which had a layer of photosynthetic cyanobacteria, I believe it was, on the surface. And there's been profile measured at different light intensities. So in high light intensity, you get a peak of oxygen here. In low light, you just get oxygen consumption. You can choose which ones you want to see, select and deselect them as you want. Now, in the activity, I think I said I would work with the one called Profile 6.1. Yeah, that fits the next slides then. So first we need to select the profile. So select which sensor it was measured with. There's only one sensor in this case, so that's easy. The profile, they're all here now. And I would like to work with the one called 6.1. That is the one with the production of oxygen in the surface layer because of photosynthesis and consumption below. And we'll see if we can calculate the rates of this. This select analysis is not, it doesn't give anything yet because I haven't done any analysis on this one. We need to fix some boundary conditions. And that is, you have to fix 2 of these conditions for the software to be able to make the simulation. What I will do here is I will choose the one called bottom concentration and bottom flux. And the reason for this is when you do that, you see it takes the bottom concentration. That was in this case 1 micromolar, and the bottom flux is 0. And this is because we can set that, but in this case I know it's 0 because we are in the area where there is no oxygen. So therefore the flux is also 0. And the gradient is vertical here. That means that the slope is 0 actually, because the vertical axis is the x-axis. Okay, so these 2 conditions are fixed. I will get back to later what you can do in other situations. Then we need to decide what part of the profile to work on. As I said, I want to work only on the part that's in the sediment. I do not want to include the water in my analysis. If you put the mouse on top of a data point, you can see the concentration and depth. And I would think that the sediment surface is around here. So let's say at minus 100. So 100 micrometer higher up than what was set as 0 here. So I would set this at minus 100. The depth to stop the analysis, that must be either this point at 1500 or maybe that one here, which if it's already 0 here, it probably is. So I'll set it at 1450. We can always change this and see how it affects us later. So now I've defined the zone I want to work with. Then the software wants to know how many activity zones it will be allowed to create. And that will make sense in a moment, but for now I'll just set it to 6. That's plenty. And it also wants to know what thickness it should use for these activity intervals. And at the moment it's set for 100 micrometer. I think we'll leave it there, and then we can change it and see how that affects the analysis. Then I need to define the diffusivity and the porosity. So I would like to work with 2 zones, one zone for water and one zone for sediment. So I increase this now to 2. The water, in my case, will then be all the way from the top of the profile down to the position I selected as the surface, and that will be minus 100. So I'll put minus 100 here. The porosity of in water, that's 100% water. Then from minus 100 down to the bottom here, which was down at 1500, it's sediment and porosity is lower. My guess is it's about 0.85. I'm not quite sure, but that would be a guess right now. See, now the diffusivity is calculated using this equation here. But I need to make sure that I've got the right temperature and right salinity, because this was measured in Limfjorden in Denmark. Their salinity is about 23. And this was the temperature. It was measured in the lab, so it's probably 22. And then the salinity is 23. And then it calculates the diffusion coefficient of oxygen in water at these conditions. And the apply button will transfer this to this window. So now we have the diffusion coefficient in water here, and we have the diffusivity in sediment here. And the confirm will then transfer. Just before I do that, I'll show one more thing. You can enter the diffusivity manually if you have a totally different way of calculating your diffusivity. Then you just enter it in these spots here. The confirm will then transfer it to the software, so it's ready. And then it's actually just to click the analyze button, and then the curve is fitted. And now you get a strange looking profile. See, first what we get here, so the green ones are the productions of oxygen, the red ones consumptions of oxygen. The orange line here is fitted to the blue measured data points. And in this case, it doesn't really make sense to have first a production, then a consumption, then a production, then a consumption. So you see, it has chosen now to use 6 depth intervals. If we go back a little up, we can go to 5. So now it's only allowed to make 5 intervals. You cannot really see the 6, but you see this one, there's a higher consumption here, slightly lower consumption there, and then 2 here, 1 here, 1 here, and 2 here. So that's 6 in total. If we go down to 5, see, now it looks different. So now it has 2 zones in the consumption and 3 different zones in the production. So the difference, so the distance between these data points, this is at 1000, this is at 1050, was 50 micrometers. So maybe the minimum width is too small. Let's look at that in a moment. You can also go back and say, well, it was 4 zones, it was 3 zones, it was 2 zones, and so on. See, now if you look at the fit between the orange curve and the blue data points, now it's not very good. So it's clearly not a good fit. This is better and this is better. So what you can play around with, then this is not an absolute science. You have to find what you think makes the most sense. You can change the depth interval. Let's say we don't want any zones that are thinner than 200 micrometer. Run the analysis again, and then you get what I think is a much nicer fit. So higher production at the surface, a lower production here, then oxygen consumption, these 3. The software itself suggests the highlighted one here, that's 5 zones. It does that based on the p-value. These statistical parameters, that's the SSE, that's the sum of squared errors. That's obviously decreasing with a larger number of zones, because you will get the fitted curve to be closer to the measured points. The p-value tells you if going from in this case 4 to 5 zones, actually made a statistically significantly better fit. And this is less than 0.05, so it did. But if you go to 6 zones, as here, the software says the p-value is 0.2, so that's clearly above the 0.05, and therefore it doesn't like that. It thinks this is the best fit. And it actually looks very well. I think it fits the points very well here and almost also here. So quite a good fit of the data points. You can, of course, if you decrease the minimum width and increase the number of zones, then you can get a profile that fits better the measured points, and you get a lower sum of squared errors. But you would want the fitted profile sort of to be an to remove some of the noise in the measurement, so to be a smooth fit of the profile, because there will be a little noise on the data points, so you want that removed. In this case, I think this is a really nice fit. Yeah, and then you can always click the save solution, and then the analysis shows up here. And now there is actually an analysis you can select here. You can then make a change and analyze, and then it says, okay, you've chosen the number of zones and the minimum width exceeds the depth you have measured. Okay, then that makes sense. So let's go down and then run this one. So now we get a different fit. We can save that again, and then there's now 2 different analyses saved here. You can select one. If you want to go back to the first one, you just do that, and then you're back in on the first one. So you can always go back and see what you have actually done when you get back half a year later and look at your data. Yeah, I think that is more or less what there is to it, except there's one more thing, and that is to export the selected analysis. And if you do that, you can, as everywhere else in the software, you can get Excel files. And I will just save this as profile and open it over here. Here it is. So you see, this is the table with all the statistical parameters. It gives you the concentration at the top, at the bottom, the flux at the top, flux at the bottom, and the integrated production. It then gives you, when I did the export, I had the 5 zones analysis here highlighted, and then it exports the 5 zones here, giving you the start position and end position for the zone with this activity, and then the start position and the end position for this one. So that means you can make a plot in your own graphing software, make a nice plot, getting these 5 different zones plotted. And then it gives you the settings you have used. It gives you the observed profile. So this is the one that was actually measured. It gives you the simulated profile. So it calculates a profile with 300 data points for you to make, if you want to make a plot of the point. And then you can see devices and so on, like all the calibrations and comments, and all what has been done. So this is, you get everything out in the Excel file, so you can use it later. And I'll just get back to the, oops, this was the one here. Yeah, just some comments. So just get the statistics right. So the p-value here, did adding this zone improve the fit? And normally I would use a p-value less than 0.05 for this. And in this case, it actually did all the way down to here, but going to this, p was higher than 0.05, and therefore this would be the best fit, similar to what we just saw. Sum of squared errors, that's this column, and they should be as small as possible, but pay more attention to the p-value than to the sum of squared errors. And look at the results and see if it makes sense. There are obvious mistakes you can make. For example, if you let the profile run too deep into the segment where concentration is actually 0, but the software sort of gets the curvature in the wrong direction here, and that gives a production of oxygen at the bottom. That doesn't make sense. So there I would I would pull up make the zone, pull the depth up, so only analyze to somewhere around here. Yeah, so there are many, you have to play around and see what makes sense. Here's an example of having 10 zones. So you see you get a very nice fit of the orange line to the blue points, but you also get a very zigzag activity pattern here. And this is because small arrows in the measurements here are translated into productions that is happening deep in the sediment where nothing should be produced. Going for instead 4 zones, you see you get a nice smooth curve that actually fits the data points well, but do not take these variations into account. So it is a smoothing of your profile and gives a nice indication of where oxygen is consumed in the sediment. If you want to work with other solutes than oxygen, so for example sulfide, you may not want to use the bottom concentration bottom flux. This one is good for oxygen because when you are down here, you have measured 0 and you have 0 flux. So that's an easy, safe way to, it's easy and safe to determine this. But you don't know that here. Instead, here you know that up here in the oxygen zone, sulfide is not present. So the flux is 0 and the concentration is 0. Therefore, you can choose the top concentration, top flux, and then set those 0. And you can let the software analyze the curvature of the profile in the sediment instead. Yeah, so basically it's a matter of playing around. You can change the boundary conditions, the depth interval you're working with. You can play around with the diffusion coefficient, see how temperature and salinity affects your measurements. And you can choose to try the different ways of calculating the diffusivity. And you can also, of course, investigate what porosity means for your rates. Export data, I've shown you this. You can choose Excel or CSV files. The Excel file will give you all the sheets in your Excel sheet, whereas if you choose the CSV file, you'll get one file for each of the sheets. So that's a bit more tedious. Yeah, so that's it. I hope this was an introduction to how to use the software, but I will be happy to try to answer your questions.
Yeah, we have a few questions, Tage. First one is production equal to net primary production?
No, not necessarily. It depends on what interval you are calculating. I'm not sure, actually. You will get the, okay, so the production calculated for each interval, yes, that is the net production or net consumption. So it may be, for example, in a photosynthetic biofilm or sediment, you may have production and consumption at the same depth. You will always have consumption if you have production. So respiration is going on, and what you get out of analyzing the curvature of the profile is the net primary production. So the excess of oxygen being produced. Yes, that's right. And can you profile in dry matter? Yeah, you can. I mean, I don't know exactly what dry matter you're referring to, but you can measure in sand or in soil or in, I don't know. In that case, you will just need to work probably with partial pressure as the unit, because concentration will not make any sense because there's nothing dissolved. Can we get N2O production rates using profiling? Yes, you can. Yes, that's just as I was explaining about the sulfide. So you'll see a production in the sediment and you will analyze the profiles. Yes, that's possible. Like manure. Yeah, okay. That was the dry matter. Well, manure depends. I don't know if it's dry matter. There may be a high, a low porosity, a high content of organic matter in manure, but you can still do it. Yes, there are quite a number of publications from Aarhus University actually on profiling in manure, both for oxygen and nitrous oxide. I think especially nitrous oxide they have worked at. Yes. Any special considerations for measurements made sub-aerially, not covered by water? Yeah, well, if there's not water and you're measuring in a gas, then flux calculations are very difficult because diffusion coefficients in gas are 10,000 times higher than in water. So it means you'll probably not see any gradients at all. Concentrations are almost the same everywhere in gas. Yeah, I don't know if that was an answer to the question. But typically, if people work in soil, they'll see they will not see a gradient if they are profiling in air-filled spaces in soil. But if they get into water, they'll see a decrease in oxygen because oxygen is consumed in the water phase and not replenished as easily as in the gas phase because, yeah, a factor of 10,000 difference in diffusion coefficient. Sediments that are saturated but no overlying water. Yes, of course you can do the calculations and the measurements there. People have worked, myself included, on intertidal flats where the surface is exposed to air. Then you just don't have any diffusive boundary layer, but you measure directly into the sediment. The curvature can still be analyzed and will still represent the net production consumption. And there was one of the publications I mentioned yesterday where they worked on intertidal flats in the English Channel or on the French side. They've actually done this, calculating fluxes on these more than 900 microprofiles they measured. So you can have a look at that, see how they've done it. Yes, we can. The question is if we have any special protection device so to make it safe not to break the sensors using in slightly pressurized bioreactors. Yeah, we have many options for that actually. You can have a look at our website. If you go to sensors and customizations, there you can see we have we can mount the sensors with a needle, hypodermic needle. We can also make it a piercing needle, so you can actually pierce rubber septors or get into a reactor. You can mount them with a stainless steel protection cap that you can mount in your reactor with a compression fitting. We can mount a 1/4-inch stainless steel tube on the sensors, which you can then also put into a compression fitting in your reactor. You can mount them in flow cells. We use, for example, the Swagelok stainless steel flow cells, 1/4-inch and 1/8 inch, where the sensors are mounted and can take a pressure to at least 10 bar overpressure. So, and you can also, if you mount them with a stainless steel tube or protection cap, they can also take 10 bar overpressure in your reactor. Yeah, so there we have different options for that. Will we avoid the data when the consumption? Oh, what happened here?
What happened?
Okay. Very large letters here. Is it possible to record a photosynthesis irradiance curve for benthic algae if I incubate a sediment at different light intensities? And how much time should I expect between individual measurements? Yeah, you can do that. And the sediment, if you have a sort of a microbial mat on top of your sediments, it is really fast. They adapt to a change in light in a few minutes. So maybe 5 or 10 minutes after you've changed the light intensities, you can have a new steady state profile. So this is and it's really fun playing around with that. We always do that on our physical workshops because it's a very nice demonstration of how short a lifetime oxygen has in such a compact sediment layer. So as soon as you turn off the light, it goes anoxic, and yeah, it's really fast. So play around with it, and it's just a matter of maybe 5 or 10 minutes between light intensities, and you have a new steady state.
There was a question above that one. Will we avoid the data when the consumption of oxygen is higher than production every time?
No, I think you can easily analyze the curvature of the profile. So, for example, if you have I'll just share my screen again because I think I could show you the one here. So there are a number of profiles here measured at different light intensities, and those here, for example, you see that light going down and down and down, and you can have a sediment in light where there's oxygen production, but you do not have a peak because the production is so low that it's cancelled out by the consumption, so you don't see the peak, even though there is a production going on. You would see it then if you turn light off completely, and you see you have even lower oxygen concentration. Then there would have been a production, and you can also measure that production actually using the light dark shift technique. One more question: what is the minimum chip size recommend? Well, it depends certainly on where you're measuring. So our oxygen sensor starts at 3 to 5 micrometer. I would not use those in a sandy sediment. There I might use a 50 or 100 micrometer instead. So it really depends. Also depends on the spatial resolution you need. So there's not a clear answer to that question, I'm afraid. Depends totally on the environment you're working in. In biofilms, for example, where there's no chance of hitting any object or whatever, then a small sensor is fine. You can do it, as small as you want, and you can get a very, very high spatial resolution. Let's stop it here. And again, thanks for participating. And let us know if you have questions or